Our next speaker is going to be Philip, who's going to be talking to us about Three.js and the future involving space, if I remember correctly. Yeah. Take it away, Philip. Let's give a hand for Philip.
Let's imagine a time long, long ago, before the internet and before the typewriter was even invented, even before those early days where you had to have your head in a clamp to take a photograph. So let's imagine that in this historical context that disposable water bottles did exist. And there was even some progress in terms of partially reusable water bottles where you could return the water bottle to get it filled, but maybe you couldn't return the cap. And this technology was really only available to the wealthiest of people. But around this time, somebody announces that they've come up with this new technology for this really large, fully reusable water bottle. And this will make water even cheaper for everybody so more people can access it. And everyone's really quite excited about this new technology. Now, while this is all going on, let's suppose that there's this major city and it has a prestigious abacus club. And the club, once in a while they get together for a meeting, and sometimes they invite a guest speaker. And one day one of these guest speakers gets up in front of the crowd and he starts sharing his ideas about building aqueducts and water towers and putting pipes in the ground everywhere. And he says that, we do this and everybody can have water piped right into their houses. So this is great. He tells the group that if they would only be willing to use their abacuses to help him do some math, that maybe everybody could have almost practically free water. And that farmers could then grow crops even if there's a drought. And possibly people could have hot baths in the winter and showers every day. So to the people of the day, these ideas might have seemed ambitious, perhaps unrealistic. So how does one convince a society to invest in a visionary infrastructure? Well, you might say, okay, we got to find some people who can move the needle on this. We need to convince them that the goal is worthy. We need to teach them how to pitch in and reward them for their efforts. But what if, it wasn't self-evident that this was a good idea? So can you imagine yourself, you're in a room and none of the people in the room understand this concept of water infrastructure, and you're trying to explain it to them. And somebody says, well, wait a second, wouldn't my house get all wet? You're piping water into my house. And then you have to explain taps. And then somebody might say, well, I don't get this tap thing, but isn't this gonna cost a lot of money, right? Or, who's gonna carry the water up to the top of the water tower every day, right? These are the kinds of questions you would get if you tried to explain this idea of water infrastructure to people. Now, for us, it's easy to understand it's a great idea, but back then, maybe not so easy to explain. All right, so this brings us to what's the Atlantis Project about. So we're this relatively small little entity on this graph of the Washington State space ecosystem, down here in the bottom, the red square. And what we're working on is space launch infrastructure, and also terrestrial infrastructure, so high-speed, carbon-neutral transportation, renewable energy, transportation and storage. So there's a few of the different infrastructure-type projects we're trying to research and promote. Now, back to that question of how do you find people willing to move the needle? Now, would you go to the merchants of water and try to convince them to build water infrastructure in all the cities? Probably not. Probably they'd go, this kind of is a threat to our business model. I don't think we want to go there with that, right? So you might think about going to talk to politicians, government politicians. Now, this is actually not a bad idea. For example, here we've got Congressman Bill Foster. He's talking to NASA about space infrastructure in a committee of the science, space, and technology. And by the way, Bill has a PhD in physics, so he kind of innately gets the idea of space infrastructure. So let's see what he had to say about the topic. Oh, I don't know if it's going to play very loudly. We might need to have audio.
The TV's finicky enough.
All right, well, I'll play it and I'll just lip sync him. Basically, he's talking to Bill Bridenstine, who's the director of NASA, was the director of NASA, and he's saying, have you guys considered investing in technologies that are not chemical rockets, so that, and he gives some examples, so that one day space access can be cheap and affordable to everybody. Have you worked on that? Is the fact that you're not working on it now, does that bother you? And what are you doing to move the needle on this? This is literally what he says. And I can show you the whole video if you want some other time. But that's what he says in this session. And then Bill goes on to try to address that question. So I would like to take a crack at explaining an idea to you, like from the perspective of today, a futuristic idea. This is going to maybe bend your brain a little bit, but I want to explain it and see how we go here, okay? So give it a chance. If you don't understand it, that's okay. It's kind of an experiment. But let's start with this idea. It's an energy storage idea. So imagine we build a ring out of, say, iron right around the equator of the planet. We put this ring inside a pipeline. We take all the air out of the pipeline. Now we need to make this ring as perfectly circular as we can. So when it's in the ocean, it'll be just under the surface of the ocean. It'll be moored to the bottom with mooring lines. And when it has to go through land, we'll actually have to tunnel through the land so that we can make this ring go all the way around the equator. And then we're going to speed this ring up so it's going at orbital velocity. So essentially it's in orbit inside this tube. It's floating. So far, this idea maybe makes sense. I don't think anybody would say that, hey, wait a second, you're violating a law of physics here, this is impossible. So far, so good, right? It's just a ring floating in a tube in orbit, but on the ground. Now, to make sure that the ring doesn't sort of bang against the sides of the tube, we'll need some maglev technology to sort of steer it, keep it in the middle of the tube. So we get that from maglev trains or from magnetic bearings. Those exist and are pretty common today. And then to speed it up or slow it down, we'll need linear motors and linear generators. So we can put energy into this ring by speeding up the linear motors, and we can slow it down with the linear generators and get the energy back out. All right, so why would we build this thing? Well, then we got to do some math. So assume this ring has a cross-section of 1 meter. If you calculate the energy using this E equals mv squared formula, the total energy is this rather large number over here, which I don't think you can see. This large number. So to put this in sort of more relatable perspective, let's divide this number by 8 billion, so the number of people on the planet. So we can think about your personal share of the energy in this ring. Okay? That personal share would be 272 kilowatt hours. Pretty decent number. Maybe that doesn't mean anything to you either, but it's a number you can relate to. Now suppose we connect up some solar panels or wind turbines, and we put energy in when there's energy to be had from renewable resources, and we take energy out later when we need it and there's no wind blowing or no sun shining. Well, if we speed up the ring by 5%, slow it down by 5%, speeding up by 5% increases this energy to 300 kilowatt hours, so there's about a total delta there of 28 kilowatt hours of storage. So that's what you get for just 5% speeding up and slowing down the ring. Now, we can cycle this power every day, which is kind of what you need to do when you're doing solar power and you want to have the power at night. You need to store it during the day for the night. And because it's infrastructure, it'll last for 50 years. There's nothing about this technology that's wearing out. It's just a big ring in orbit. So you can probably cycle this thing 18,250 times, which is the number of days in 50 years. And then we're going to calculate what this storage is worth to you personally, just your personal share of the storage. So if you had to get that same storage by buying Tesla Powerwalls and then replacing them and recycling them every time they wore out for 50 years, Tesla Powerwall costs 41 cents per kilowatt hour cycled. That's what the math shows in this bottom corner here. If you do the same math with this ring, it turns out it's worth $209,000 for the Tesla Powerwalls. So this isn't too bad. You've got yourself a piece of ring that's 5 millimeters thick. That's your personal share. About 1 meter in diameter. It's like the size of a coffee table. It's just steel. And this thing is turned into infrastructure, and now your share of this thing, which is that piece of steel, is worth $200,000. You could buy a house with that. Because the ring is going around the planet so fast, you can actually put energy in on one side of the planet where it's daytime, and you can take it out on the nighttime side. And the energy was taken right around the planet by the ring for you. And so, in fact, you can take the speed of the planet rotation divided by the speed of the ring's rotation, and that gives you an additional factor, which makes that $200,000 become worth $1.7 million. So this storage is actually $1.7 million for you personally and every other person on the planet. This is the power of infrastructure. This is what sort of thing we can do when we sort of make a big idea happen together. So that is quite cool. But there's still some ways you can make this even better. So for example, right now this thing is on the equator and it's got to go through mountains and things. What if you don't live in the equator? It's not much use to you, right? Well, you can actually make rings that go up and down the planet like this, The only challenge here is that the rings that are not on the equator, they're going to tend to fall towards the equator if they're just floating in the tube. So those magnets that keep the ring in the middle of the tube have to work a little harder. So you have to make sure there's a uniform magnetic field for them to travel in. But again, that's not too difficult. I think the guys at CERN who make the particle colliders could figure this kind of thing out. And then, well, you know, do you really need to have it go through all the land? Could you build it in the ocean? It turns out you can build this ring in the ocean, put it on the side of the planet. That means that you don't have to tunnel to make this thing anymore, so it gets cheaper to build. But now you're saying, well, it's not anywhere near anybody, it's in the ocean. So what you can do next, you can actually lift this thing out of the water. This diagram here, this little video, which by the way was made in Three.js, which is kind of why I'm talking about Three.js, shows how you could lift this ring out of the water, and once you lift it out of the water, you can move it around the planet to some location where it's needed. So these are all refinements on that original idea of a ring on the equator to make the idea cheaper and more realizable. Although it starts to get a little harder to believe, I'm sure you can say, right? Okay, so this is another picture of it from closer up, just showing how it's lifted out of the water. So I don't know if you followed all that, but just think of it like me trying to explain water infrastructure to people 200 years ago. Here I am trying to explain an idea that's in the future to a bunch of people who have never probably worked with power, renewable power. Actually, if you have worked with renewable power, raise your hand, because that would be interesting. You have, we got one person. Right, so you understand the value of intermittency and storing energy, right? Good, okay. I got a nod in the corner. There's another approach to this problem. You don't have to go straight to building a big ring. You can obviously start by building smaller rings, which aren't quite as efficient in terms of their energy storage capability as a huge ring is. It's a good way to get started as say, a small company and work your way up. But another way to do it is to build a digital twin of your idea and try to explain it that way, which is what this talk is really about. Okay, so I've talked a bit about this carbon neutral storage idea. I'm going to breeze through some even crazier ideas that are a little harder to follow, just because I want to give you an appreciation about the challenge here when we're trying to convey an idea to an audience. You can imagine you were an investor and I wanted you to pull your wallet out at the end of this meeting or your Venmo and give me $1 million. You know, you got to be convinced, right? So that's a challenge. So the next idea is related to carbon neutral transport. So right now there's really two options. If you want to go a long distance, you can either take an airplane or you can take a high-speed electric train. If you take in the airplane, what's good about that is their corridors are free. They travel in the stratosphere, nobody charges them for doing that. But then they gotta have airports, they burn fossil fuels, they're pretty expensive, they've got landing gear, wings, all kinds of stuff, pilots, flight attendants. The other way is traveling on the ground with a high-speed train. Then you get to electrify it, which is great, better for the environment, but they've got corridors you've got to pay for, and they're very expensive. Like the land, you got to buy the land, you got to do environmental studies, or dig tunnels, or build viaducts. There's a lot of cost in high-speed trains, and they're not as fast as planes either. But what if you could blend these two ideas and take the best elements of both? So if you could put a transit system in the stratosphere, you get the benefits of electrifying the transit system, and also you have free corridors. So this is what this idea is about. That tethered ring I described, lifting it off the ground, you can use that to support a transit system in the stratosphere, and then this transit system can be very affordable to travel in. So there's some diagrams of what this looks like. There's these vehicles that travel inside a hydrogen-filled tube. You can go at 5,000 kilometers an hour inside a hydrogen environment at that altitude without breaking the speed of sound. So this is very, very useful. Very fast. Some animated versions of how this looks. These are some diagrams about the pros and cons of airlines, transit system, and this stratospheric system. And this is a calculation of cost per available seat mile or kilometer, cost per available seat kilometer, and it shows how the transit system in the stratosphere is actually cheaper per available seat kilometer than the other kinds of transit. That's this green line at the bottom compared to the blue line and the orange line. So I know that's too much for you to absorb in one short session. This is like, that presentation alone would be like a 1-hour presentation in most technical conferences, but I want to give you a quick idea of that one. The next one I want to talk about quickly is carbon neutral space launch. So this idea is about accelerating a space vehicle on the ground up to orbital speeds, have it travel travel on a ramp and then through an evacuated tube up to the top of the stratosphere. So this evacuated tube is supported by this tethered ring. And then you can go off into space by traveling to the remaining rarefied atmosphere. And again, we've modeled this in Three.js. I've got some figures here to show you This is a bit about hypersonics, a graph showing different things we've done in hypersonic speeds and where this would fall in relation to them. And this is the mass driver image. And some ideas here about how it actually would work. So again, if you're interested in this kind of thing, want to know how it works, and want to actually see if it's true or not, if you can believe this or not, come and see me afterwards and get into more detail. There are like large papers in explaining all this, 20-page technical papers. If you're interested in reading them, that'd be awesome. Here's another figure of that. Okay, so now you get an idea. You got this guy up here who's talking all kinds of crazy stuff, and you can now probably appreciate how hard it would be to convince the general public to believe in these ideas and how much they would be worth to the general public if we could get everybody to invest in them. So the challenge, of course, is how do you convey these ideas? How do you actually get people to take the time to read the papers, check the math, believe in the ideas? This is hard. This is a hard problem to solve. The strategy that we've been using, for the most part, is the development of what we call a digital twin. Now, other ideas out there, like you've probably heard of a space elevator. Who's heard of a space elevator? Yeah, so everyone's heard of the space elevator. Has anybody ever seen a digital twin or a mathematical analysis of the space elevator that proves it works? Not a single hand in the room, right? It's because if they publish that, it would quickly show that it doesn't work. It's not a viable technology. The same thing for space-based solar. This is another technology where people, has anyone heard of this idea of space-based solar? Again, well, one person, that's not as many. Two people? Okay. But again, you can't find any, you can find some, but you can't find any publications on that explaining why it works, because it's not that viable a technology. So we're trying to get past that by actually publishing on GitHub an accurate model called a digital twin of these technologies. And the advantage of that is that somebody can, first of all, visualize what it is we're talking about a lot better, because we're not just waving our hands, they can see it. Secondly, they can actually go into the code, because it's on a web page. They can put a breakpoint, they can look at the math, they can even go in and change parameters. So we've got some 600 parameters here that you can expand and go in. So if you don't like an assumption that we've made around something like the cost of carbon fiber or something like that, you can say, I don't believe that number, I'm going to change it and check your math again, so that people can engage and check everything themselves. So this is the idea behind digital twin, and this is what we've been working on in JavaScript and Three.js. So that's kind of cool. It's this tool for conveying to more and more people, hopefully, that these ideas are real. One of the things that we're also doing is taking some of the code from the digital twin and giving it back to the Three.js community. So we're trying to create an example here with some of the code turning into a smaller version that other people can just study and work with. So this is a bit like a Google Earth type thing, but inside Three.js. So you can make your own, theoretically, you could make your own Google Earth if you got this example, if you borrowed our example and it works. And then for us, the digital twin does things like it helps us check our math and avoid making mistakes in papers and things like that. It helps us to communicate. We can generate images and video clips from it. We can even generate graphs to help explain costs and things with the digital twin. And it helps us refine our ideas. So sometimes we produce something, we look at it and go, yeah, that doesn't look like it really would work. So we refine the idea and come up with a better idea over time. So for example, those tubes that I showed before, they used to be evacuated tubes. And we started using the digital twin to sort of analyze that and figured out that they would probably collapse or be too heavy if they were evacuated tubes. So we thought about it and then said, let's fill them with hydrogen and see what that gets us. And hydrogen tubes are much lighter. Our hydrogen-filled tubes are much lighter. They don't have to deal with the pressure of the atmosphere outside, so it turns out to be a much better idea. Now, back to the abacus club idea. Suppose, I wanted you to get your abacuses out and help me out, right? So what would be in it for you? Why would you want to do this? Well, one reason is you get exposure to some of the programming techniques that are being used in the model. There's some very advanced techniques in here. So we have like dynamic allocation of the models. We have techniques for rendering things over planetary scales, which is an interesting, challenging thing to do. We can manage hundreds of parameters, and we have special tools and techniques for doing that. We have tools for capturing images and video. We can export some of these models to Google Earth, so you could actually see the same thing in Google Earth as a KML model. And we also have a VR mode, which we're not using too much. It's still sort of rough, but it does work, so you can experience this whole thing in VR as well. So these are just some of the things that the model has. It's a lot of code. But it would be really cool to have more people getting involved in it and helping you bring your own knowledge to it. The other thing about what's in it for me is if you're just starting out and you're independent, but you lack experience, and you're having a hard time finding a job, right? You might settle for a crappy job, but if you were to, work on a project like this and then go to a job interview at a really cool company, that hiring manager is going to probably remember you if you start talking about this project and what you did on it, because this is a memorable kind of thing. So there's a better chance that you're going to make it through that job interview phase and get hired by the really cool company, which means you'll make money faster and be able to retire earlier, which is really cool too. And you'll have fun while you're at the job, I think. Anyway, and the other thing is, if you're at the end of your career, more like I am, and you're ready to retire, this is a great way for you to sort of keep working, keep your skills fresh, and hopefully find a way to contribute to the future of society and make our planet a greener place, safer place, more sustainable place in the future. Possibly even settle Mars. So we'll see how it goes. All right, these are some links for resources if you were interested in learning more. But if you have any questions, feel free to do we ask now? Afterwards. You can ask questions afterwards, but not now, according to Andrew. All right, thanks very much.